So you know the formulas, right? You get the concepts. But then quiz day comes and bam, you're losing marks to what feel like just silly mistakes. A sign error here, a unit mix-up there. It's incredibly frustrating. Well, today, that stops. Let me throw a number at you. 8. That's the average number of marks that just evaporate on electromagnetic induction questions because of these simple, avoidable errors. These are your hard-earned marks, just slipping through the cracks. So today, we're going to change that. Think of this as getting your immunization shot against the CBSE's 5 deadliest traps. We're going to expose them, understand why they work, and build a system so you can see them coming a mile away. Let's turn these weaknesses into your biggest strengths. All right, let's dive in. The first couple of traps are honestly the most dangerous. Why? Because they're not about messing up a calculation. They're about a fundamental misunderstanding. If you fall for one of these, your whole answer is wrong before you even start calculating. Okay, trap number 1. It looks so simple, right? The difference is literally one word, change. But come on, this is physics. That one word changes everything. And trust me, this is the single most common way students get Lenz's law wrong. So here's the fix. You have to think change. The induced current is like a stubborn mule. It's not fighting the magnetic field itself, it's fighting the action of changing it. Is the flux increasing? Boom, the current creates an opposite field to push it back down. Is the flux decreasing? Well, the current creates a field in the same direction to try and prop it back up. It always opposes the change. Okay, on to trap number 2. And oh, this one is a classic. It's so easy to think that EMF and current are like a package deal, you know? Like if you have one, you must have the other. But that's just not true, and you can bet the examiners know this and love to test you on it. But you might be thinking, okay, that's a subtle point. How does this actually show up on an exam and trip me up? That's a great question, because it appears in questions that are designed to look super simple, but are hiding this exact trap. And here's a perfect example. Check out this assertion reason question. You've got a magnet falling through a copper ring, but look closely. The ring has a cut in it. That cut makes it an open circuit. So let's break it down. Is an EMF induced? Absolutely. The magnetic flux is changing as the magnet falls. But, and here's the trap, does a current flow? Nope, there's no complete path for it. And if there's no current, there's no opposing force. So the magnet just follows freely. Simple as that. Here's the easiest way to lock this in your brain forever. Think of EMF as water pressure. Imagine a pipe with the top closed. There's pressure in there, right? That's your EMF. But is any water flowing? No. Current is the actual flow of water, which only happens when you open the tap and give it a path. Open circuit, pressure but no flow. EMF but no current. All right, we've handled the conceptual traps. Now let's talk about the calculation traps. This is where the numbers can betray you. You've got the concept down, you've picked the right formula, but one tiny slip up and poof, all your marks are gone. And let's be clear, we're not talking about a small rounding error here. Forgetting to convert 20 centimeters to 0.20 meters doesn't just make your answer a little bit off, it makes it 100 times wrong. It's not just an error, it's a fatal flaw that makes the entire answer useless. So how do we fix this? With a simple 3-step protocol. And this is non-negotiable, you have to do it every time. Step 1, scan the question and circle every single unit you see. Step 2, before you even think about writing down a formula, write a separate line just for conversions. Convert everything to standard SI units, meters, seconds, Teslas, the whole deal. Step 3, only then do you substitute those clean converted numbers into your formula. Make this a habit, and I promise you, it will save you so many marks. Okay, trap number 4. This one targets a really common misconception. We know inductance, whether it's L or M, has something to do with current, right? So if I double the current I'm pushing through a coil, does its inductance also double? The answer, a huge, resounding no. It does not. Think about it like this. An object's mass is an intrinsic property. It doesn't change just because you throw it faster. Inductance is the same. It's all about the geometry of the coil, how it's built, its shape, its size, not about what you're currently doing with it. And if you don't believe me, just look at the formulas. Let's take the self-inductance of a solenoid. What's in there? Turns per unit length, area, length. Now look at mutual inductance. Same deal. Turns, radius, length. Do you see an I for current anywhere in these equations? Nope, it's not there. Inductance is defined by how you build the thing, period. Okay, let's move on to our final big trap. This one isn't about a tricky concept or a math error. This is about the hardware, the actual components. Specifically, it's about confusing two parts of a generator that look kind of similar but do completely different jobs. I can almost guarantee you'll see a one-mark question on this. Let's break it down. Slip rings. These are two solid, continuous rings. Their only job is to get the current out of the rotating part smoothly. They give you a standard AC output. The analogy? They're like wedding rings, smooth and continuous. Now the commutator, this is one ring that's been split in half. Its special job is to flip the connection every single half turn. This is what turns the AC inside the generator into a DC output outside. Think of them like two half-moon cookies. They're split. Totally different things. All right, we've covered the 5 big ones. To finish up, let's do a rapid-fire round of bonus traps. These are smaller mistakes, but they're super easy to make when you're under pressure. But they're also super easy to avoid if you're looking for them. First up, N versus N. In all those solenoid formulas, big N is the total number of turns, but little n is the turns per meter. The fix? Always calculate little n by doing n divided by L before you plug anything into the main formula. Next, the missing half. It is so easy to forget the half in the energy formula, U equals 1/2 Li squared. Here's a quick tip. Think about other energy formulas in physics. For a spring, for a capacitor, they almost always have that 1/2 in front. Don't let the inductor be the one you forget. And last one for the bonus round, the angle error. In the flex formula, phi equals BA cos theta, you have to remember that theta is the angle to the normal. That's the line sticking straight out, perpendicular to the surface. It is not the angle to the flat surface of the coil itself. That's a classic mistake. So, we've been through a lot of traps. What does dodging all of this actually get you? What's the real payoff? Well, it's not just about fixing a few mistakes. It's about a serious upgrade to your final score. Let me show you what I mean. Look at this. Avoiding these 5 major traps, plus those little bonus ones we just covered, that's not just a couple of extra marks. It's easily the difference between scoring a 70 and scoring an 85. It's what takes you from pretty good to absolutely crushing it. This is how you gain a real strategic edge. So, you've now got the defensive playbook. You know how to protect your marks from these common traps. But what if you could go on the offensive? In our next explainer, we're going to build your attack plan. We'll walk through the common CBSE question patterns and figure out the best strategy for tackling them. You're ready to stop just defending and start attacking the test. You ready?